Welcome to EDU World Space.
Okay, so we're doing chapter 32, problem 70. So it says a coin lies at the bottom of a 0.75 meter deep pool, and the viewer sees it at an angle, at a 45-degree angle. Okay, where is the image of the coin relative to the coin? Cool. So the hint it tells us is the image is found by tracing back the intersection of two rays. So if we look over here at this diagram, we have this little black puck here is the coin. If we look at two rays from two similar angles, an angle of phi and an angle of phi plus d phi from the vertical, they come and get refracted at angles theta and theta plus d theta. And then if you retrace those refracted rays, we should get an image over here roughly. So our job now is to figure out where exactly is this image. So to start this off, we're going to do Snell's law to both of these two rays at the leaving the interface of the water-air interface. So we should be left with n sine phi equals n sine theta for the first ray, and n sine phi plus d phi equals sine theta plus d theta. Cool. So now we can simplify these using some good trig identities, and we can write sine phi plus d phi as sine phi plus d sine phi over d phi times d phi. If you simplify this out, we should see that this is sine phi cosine phi d phi. Okay, so we can do the same thing with our sine theta plus d theta and set this to sine theta plus, sorry, this is a plus here, plus cosine theta d theta. So now, if we plug these relationships into our Snell's law equation and solve, we have a relationship between the differentials, which we call a Jacobian relationship. So we have a d phi is equal to cosine theta over n cosine phi d theta. Cool. So this will be very important for us to use later. So now let's do some geometry. And let's draw this here as the x-axis and this as the y-axis, with the coin being at the origin. Also y, not an x. So we should see that for ray 1, it leaves at an x1 of h tan phi, and y1 equals h. Cool. So now let's plug that into the equation for a line and solve for it, and we should see we have the equation for this line, the traced back line of ray 1, will now be we gotta figure out what n1 is first. What is n1? That'll be the slope of the line. We have the 2 points, but we need a slope, or we have the point, but we need the slope here. So n1, the slope of this line, this can be given as the cotangent of theta, because this is the rise over the run here, but we want the other way around, so we'll take the 90 minus, or tangent of 90 minus theta, and that's also the same as cotangent theta. So if we plug this in now, we can get our equation to be h plus x minus h tan phi, and then times the slope, and our slope was n1, and that's cotangent theta. So that's the traced back equation for the first ray. So now we're going to have to do the same thing for the second ray, and this is going to be a little bit more challenging here. So we got to figure out the second ray, ray 2 here. Where does this lead from? So x2 is doing some geometry. We see that this is h times the tangent of phi plus d phi. And y2 is, again, just h. If we do our similar tricks we had before, we can set x2 equal to h times tan phi plus secant squared phi d phi. Cool. So that's our x2 and our y2. So we got to figure out the slope here, and this will be done in this similar way of tangent of 90 minus the angle here, but that is now theta plus d theta. So if we simplify this out, we can see that this is going to be cotangent of theta minus cosecant squared theta d theta. That's just with some trig identities and some differential stuff. We see cotangent theta, cosecant theta, d theta. Cool. So again, we can plug this into our equation for the line, and we see that we're left with y equals h plus x minus h tan phi plus secant squared phi d phi. And this and multiplied by our slope, cotangent theta minus cosecant squared theta d theta. Cool. So now we have both of these lines. So to find out where they intersect, we just set the two expressions for y equal to each other. So we're going to set this equal to our one up here. So that was h plus x minus h tan phi cotangent theta. Cool. So now that we have these equal, we can see these h's are going to immediately cancel out. And if we expand the terms and then subtract common terms, we get the following. We should get x cosecant squared theta d theta equals h tan phi cosecant squared theta d theta minus h secant squared phi, and this is d phi cotangent theta plus h secant squared phi d phi cosecant squared theta d theta. So immediately we should see that this has two differential terms in it, so that's going to be very small and we can neglect it. So that'll simplify us a little bit here. So if we delete that and also bring in this relationship, we can simplify this a lot. So let's write this relationship again. So this is, go to second page. So we have a relationship d phi equals cosine theta over n cosine phi d theta. Cool. So let's plug that, use this relationship in and plug that in for d phi. And we should solve this to x cosecant squared theta d theta equals h tan phi cosecant squared theta d theta minus h secant squared phi cos theta over n cos phi d theta cotangent theta. Cool. So now we just solve this out and we see that the x is equal to h tan phi minus secant squared phi cosine theta over n cos phi cotangent theta over cosecant squared theta. Simplify this a little bit more. This is h tan phi minus cosine squared theta sine theta over n cos cubed phi. Cool, we're getting there. Now we can just plug in numbers for this. So we know that theta equals 45 degrees, h equals 0.75 meters. So we can immediately solve for some stuff. So using the first sine laws expression, we know that phi must be the inverse sine of theta over n. And this should be 32.12 degrees when theta is 45 degrees. So theta equals 45, that equals that. So let's go into a new page here. So if we know that theta equals 45, h equals 0.75, phi equals 32.12, plug that all into the equation for x, and we see this is 0.1427 meters. Awesome. Lastly, we can just plug this in our other equation, and we see that y equals h plus x minus h tan phi cotangent theta. So this equation is a little bit easier to plug in now that we have our stuff. And if we plug all that in with these parameters up here, we should see that this comes out to being 0.4264 meters. Cool. So coin is at 0, 0. Image is at 0.143, 0.426. Cool, so that's slightly above and closer towards the viewer. Awesome.